So hello everyone and welcome to my talk. My name is Balázs Ráth. I'm from the Department of Stochastics at the Institute of Mathematics of Budapest University of Technology, and I'm very grateful for this opportunity that I can talk on the Wigner Research Seminar. I hope you can hear me well. And before I begin my talk, there are two things that I would like to mention. There are two ways for you to make me happy. One way for you to make me happy is that you look at the description of this live stream video, and you can see an online form, and please click on it and enter your name, your affiliation, and these things. This is rather important for me, so if you want to make me happy, please give your name and the university that you're attending and what kind of student you are. This is important for a scholarship of mine. The second way to make me happy is interaction, and our only way the only way for you to interact with me is via the chat. There's a chat wall, and if you, let's say, if you can hear me, please write something. Okay, please write something now so that I can see that I'm talking to someone who hears me. Okay, anyone. I know that there's a bit of delay here, but any, okay, great. Something. Okay, that's great. So let's start with the talk. This talk is about forest fires and some random graphs that evolve in time. This started as my PhD topic more than 10 years ago, but I keep on working on this, and as a matter of fact, the main thing that I will talk about today is very recent. So this is I'm going to talk about a paper that's under revision right now, so let's see. Well, let me start with a philosophical question. So a long time ago, so the question is how to avoid a catastrophic forest fire, and this started a long time ago. Back in 2002, I was in the US, in California, in a sequoia forest. So sequoias are these huge pine trees, and I was there in this forest, and the people, of course it was a national park, and they told us that they were protecting this forest from fires, and they have already spent 100 years protecting this forest from dangerous fires, and as a result, so much inflammable material have built up in the forest that now anyone throws away a matchstick that will cause a very dangerous, huge fire. So somehow, if you're overprotecting your forest, then somehow that will cause a very dangerous situation. So if you put out all of the fires immediately, then somehow the inflammable material will build up, and that will allow the fire to kill a huge chunk of the forest. On the other hand, if you allow small fires to burn some small parts of the forest, then these small fires will keep the forest from entering this dangerously inflammable state, and therefore, if you do not put out the small fires, you can avoid the big fires. And like philosophically, if you leave the forest alone, that is the safest way of protecting the forest from very dangerous fires. And of course, small fires will occur constantly, but they will never allow the forest to enter such a dangerous state. So that was the message there that I obtained, and today's talk is going to be about this phenomenon. Today we will learn what happens if you leave the forest alone. And what happens is this nice phenomenon called self-organized criticality, which in pure words says that the forest kind of keeps itself in a state which is on the borderline of catastrophical and safe, and organizes itself in a way that it's not allowed to enter the dangerous state. But of course, we will need many mathematical definitions, but by the end of the talk, I very much hope that you will get a more mathematical understanding of this phenomenon. So I'm going to define a mathematical model of forests. Namely, it's going to be a graph. So there is going to be this graph denoted by G and T, and it's going to be a graph on n vertices, and it is the edge set that's going to change as the time evolves. So the vertex set of this graph is going to stay the same, but the edge set is going to change over time. So you can think about these vertices of the graph as trees, but it's more like these edges appear between these trees. So at time t, a possible edge of the graph can be occupied, present, or vacant, and these edges between these vertices, this is where the fire can spread. So imagine these edges as inflammable, and if you set on fire one endpoint of this edge, then immediately the fire is going to spread along this edge and kill and destroy the edge, and as a matter of fact, it's going to destroy the whole connected component of the vertex where the lightning has struck. So okay, so back to the definitions. So the inflammable edges appear spontaneously, so this forest grows, the inflammable material starts to build up, but then sometimes, occasionally, lightnings strike the vertices, and then the fires spread along the edges, and the fire burns the connected component. But then the forest keeps on growing, new edges might appear, so edges appear and disappear, but the number of vertices is going to stay n throughout. And there is going to be some sort of balance of creation and destruction, which is going to create this self-organized criticality that I mentioned at the beginning. Okay, so just for fun, so here's a little movie about what's going to happen. At the beginning, you have these vertices of the graph, and there are no edges. But then, as time elapses, one edge appears, and another one appears, and yet another one appears. So now the inflammable material builds up, and now we have one connected component of size 3, there is another connected component of size 4, and of course that's more dangerous because look, there's a little red dot there that signifies a lightning. So a lightning struck this particular vertex, and now immediately the fire spreads along all of the edges of the same connected component and deletes the edges. And of course, the fire, this was a little bit of a catastrophe there for the forest, but of course, after the fire, now the forest is in a more safe state because now there are less edges to burn. And of course, as time keeps on going, new edges are going to appear, etc., etc. So this was a little movie, but now let me go on in a more rigorous fashion and define this model. So this is going to be a Markov chain. So this is going to be a stochastic process. So things are going to happen at random. And let me try to describe the dynamics of this graph GNP. So first of all, there are n vertices and there are n choose 2 possible edges, and any of these possible edges might become occupied. So in the language of physics, this is a mean field model, so there is no geometry. That is because we are doing mathematical modeling, and this is easier to tackle. Of course, in real life, forests have geometry, and let's say there is a two-dimensional underlying geometry. But for the sake of this talk, we ignore that and talk about the mean field setting, where any two vertices can be connected by an edge with the same probability. So, as I was saying, this is a stochastic process, so things evolve in time. Namely, if there is a vacant edge, then it becomes occupied at rate 1 over n. So this is a very small rate. The rate is the reciprocal of the number of vertices of the whole graph. And this is creation, and now let's see the destruction part. The destruction part is that each vertex gets hit by lightning at rate lambda n, where lambda n is a parameter that we are going to tune a little bit. And then, as I was saying, if a lightning strikes a vertex, then fire spreads along the occupied edges and burns them immediately. And therefore, if you strike a vertex with lightning, then the whole connected component is going to be deleted. What I mean, the edges are deleted. So effectively what happens is, if you delete a connected component of size 100, say, then it's going to be immediately replaced with 100 vertices that are singletons, that are not connected to anything else. So, so this was the language that vacant edges become occupied at rate 1 over n, and vertices get hit by lightning at rate lambda n. So this is a language that some of you might be familiar with, but probably not everyone. So let me try to rephrase it in a language that's maybe a bit more familiar to most of you. So now I'm just going to tell you the same thing using a tiny bit different language. So this is I'm going to use the language of Poisson point processes. Namely, every edge, every possible edge, has a Poisson point process on it, and the intensity of this Poisson point process is 1 over n. And if there is an arrival of this Poisson process, that means that that edge becomes occupied. But of course, if it's already occupied, then nothing happens. And similarly, every vertex has a Poisson point process with the intensity lambda n on it, and at each arrival of that Poisson point process, the vertex gets hit by lightning, and this burning event occurs. I hope you're familiar with the notion of Poisson point processes. At least I'm teaching it, or well, you know, there's a course this semester, the Probability 1 course, where you can learn about it. Of course, and we delete all of the edges of the connected component of the vertex that got struck by lightning. So this is the forest fire model. My talk is about this model and the strange self-organized critical behavior that this model exhibits. But in order to explain that, I have to talk about something simpler. Namely, I have to talk about the model where there are no lightnings, and this is called the ErdosRenigraph, or dynamic ErdosRenigraph. So this is a famous object that was invented by two Hungarians in the 60s, and I'm going to abbreviate it by like this. So ER means ErdosRenigraph. So let me describe what it is. It's just the previous model without lightnings. So if the lightning rate is 0, then you have Erdős-Rényi model. So of course, as you have seen before on my little movie, you start with the empty graph on n vertices, and there are n choose 2 possible edges, and each of those edges, if they are vacant, then they become occupied with rate 1 over n. And effectively what this means, that the time when one particular edge becomes occupied, this time has an exponential distribution with the rate 1 over n. So the parameter of this exponential distribution is 1 over n. And of course, this exponential random variable, which describes the time at which this edge turns on or becomes occupied, these random variables are independent for different edges. Okay, and let me stop here and ask a little question about exponential distribution to check that you're not sleeping. So what is the expected time when a particular edge turns on? Okay, so if you have an exponential random variable with parameter 1 over n, then what is the expectation at which this particular edge is going to become occupied? So please write it in the chat box. Okay, so the winner is Miklós Eper, who told me that the expectation is n. So of course, n is very big. Maybe I did not mention that, but this n that I'm talking about, the size of the forest is big. So you have to wait for a very long time for one particular edge to appear, but that's fine because there are many edges to be turned on, so don't be afraid. This is going to be the action is going to take place in normal time. You don't have to wait for very long to see something interesting. So in particular, if you have an exponential distribution with parameter 1 over n, then of course you know the distribution function of exponential distribution very well. So this means that at time t, each particular edge is occupied with probability 1 minus e to the minus t over n, and of course it's vacant with probability e to the minus t over n. And of course this event happens independently from other edges. So this graph on n vertices whose edges are present independently from each other with the same probability, this is Erdős-Rényi random graph, classical object. And now we are going to learn a little bit about it. Maybe now I'm going to bore some of you because you have already learned about Erdős-Rényi graph, but it's always useful to repeat what you know. And here's a little reminder that e to the minus t over n, I mean 1 minus e to the minus t over n is roughly equal to t over n if t is very small. So of course both of these numbers are very small because I imagine that t is not very big, but what comes later in my talk, I'm going to casually replace these probabilities by t over n. So I want to talk about the Erdős-Rényi graph, and I want to figure out what happens to an Erdős-Rényi graph if I hit it with one single lightning at time t. I want to see what kind of destruction I impose on this graph if I hit it with one single lightning at time t. And the language is, so in graph theory we call what we call a connected component. In this talk I'm just going to call it a cluster. So that's just the terminology that people usually use in this context. And I want to introduce a little bit of notation. So if there is a vertex v, then I want to denote by cv of t the connected component or the cluster of the vertex v in this graph G and T. And of course, if I hit this vertex V with a lightning, then this whole connected cluster is going to be destroyed. And I will also be interested in the size of the biggest cluster, the largest, the one with the most vertices, and I'm going to denote it by C max of T. So this is the biggest cluster in the graph. You might ask, well, what happens, Balázs, if this cluster is not unique? But I don't care. Usually, if the biggest cluster is small, then there might be many clusters with the same size. But if it's big, then there is going to be a unique biggest cluster in the graph at time t. So just a reminder, right now G and T denotes the Erdős-Rényi graph. And here is the famous phase transition of the Erdős-Rényi graph, which says that there is some sort of radical change in the size of the biggest component as time elapses. And you should imagine that T is fixed and N, the number of vertices, is very large. And here's the theorem of Erdős and Rényi. So if the parameter T is less than 1, so before time 1, the graph is in a subcritical phase, namely the connected components are small. For example, if you look at the expected size of the connected component of your favorite vertex, then this is going to be 1 over 1 minus t. So in particular, it stays bounded no matter how big you choose n. Remember, of course, the graph gets bigger, but the probability that a particular edge is present is t over n. So there is some sort of balance, and this expected value is going to be roughly 1 over 1 minus t if n is very big. And also the size of the biggest component is not very big either. Some of these components might be so lucky that they reach size log n, but only very few of them. So in the subcritical phase, the sizes of the connected components are very small. So in particular, if you hit a subcritical Erdős-Rényi graph with one lightning, then this lightning is not going to destroy too much. So one lightning would destroy only a few vertices. The expected number of vertices that one lightning destroys is this quantity here, 1 over 1 minus t. And well, actually it does not really even destroy the vertices. It's more like it destroys the edges of that connected component. But on the other hand, if t is strictly greater than 1, then you see something radically different. Then your graph is in the supercritical phase, and actually there is a giant cluster, there is a giant connected component, and the size of that giant connected component is comparable to n. There is a connected component whose cardinality is a positive fraction. So like the giant component contains a positive fraction of the vertices of the graph. This is something radically different. Of course, if t is only a little bit bigger than 1, then this fraction that I denote by theta t, this fraction depends on t, but as soon as t is greater than 1 and n is very big, then what you will see is that the fraction of vertices contained in the giant component is positive, and therefore the probability that a particular vertex, your favorite vertex, the probability that this vertex is in the giant component is of course roughly equal to this fraction. And of course, if you hit your favorite vertex with a lightning, so if a lightning strikes one of the vertices that's in the giant component, then of course it's going to destroy the whole giant component all at once. And this is what I call a catastrophic fire, because one single lightning caused a positive fraction of my forest to burn down. So this is a very big change that happens at t equals 1. And by the way, if you're exactly at t equals 1, this is called the critical point, and this is the strangest thing, the strangest state that this graph can be, because in this state, the size of the giant component is already bigger than log n, but much smaller than n. And similarly, the expected value of the size of the connected component of a particular vertex is already much bigger than 1, but it's still much smaller than n. As a matter of fact, it's much smaller than the size of the maximal component, because at this point, the maximal component is much smaller than n, so your particular vertex is with high probability, it's not in the giant component, but still it has a big expected size. So this is the critical point, and I don't want to talk too much about it. The only thing that I want to say is that there are these two phases. The subcritical phase, which is safe in terms of forest fires. There is the supercritical phase, which is dangerous in terms of forest fires. And there is one single time separating the two phases, and that's called the critical point, separating the subcritical and supercritical phases. So this was a little crash course on the Erdős-Rényi, and here's a little proof of the things that I just explained. So this is not a proof, this is a heuristic argument, but it's going to be enough for the purposes of this talk. Namely, let me denote by zk of t the number of vertices at distance k from my favorite vertex v in this graph. Then of course, z1 of t is simply the number of neighbors of vertex v. And let's try to see the size of this set. Let's try to figure out the number of vertices that are neighbors of my favorite vertex. And of course, this z1t has binomial distribution with the parameter n-1, and now I'm cheating, so it's t over n, so I replace the edge probability with t over n. Why? Because it has n-1 possible neighbors. Each of them are actually a neighbor with independently from others with probability t over n. So by the definition of binomial distribution, this is the number of neighbors of my favorite vertex. And in particular, it's well known that the expected value of a binomial random variable is just the product of the two parameters. That's going to be n-1 times t over n, and that's roughly equal to t, because I'm still assuming that n is huge. So the expected number of neighbors at time t is roughly equal to t. And so what is the expected number of second neighbors? So z2 is the number of the neighbors of my vertex v, so the cousins. So the neighbors of neighbors, but not myself. So the new neighbors of the neighbors of v, those are exactly the points which are at graph distance 2 from my favorite vertex. And it's not hard to believe that the expected number of cousins is going to be t squared, because there is the expected number of neighbors is t, and each of them has an expected number of t new neighbors, roughly. Then therefore it's t times t, so it's t squared. So this is kind of a hand-wavy argument, but I trust you to believe me. And similarly, if you look at the number of vertices at graph distance k from my favorite vertex v, then it's going to be roughly equal to t to the power k. There is certainly an error term here that depends on n, that depends on the size of the graph, but if you imagine that k is small, and n is very big, then this is a reasonable approximation to approximate the expected size of my kth cousins by t to the power k. And now you can already see why there is a big difference if t is less than 1 and if t is greater than 1. Because, of course, the connected component, the size of the so this is the size of the connected component of vertex v at time t. That's, of course, the sum for all possible distances, the number of vertices at distance k from my graph. If I sum for all possible values of k, then I obtain the number of all of the vertices in my connected component. And of course, if I take the expectation of this identity, then I get an equality. And then if I use the linearity of expectation, then I get this dichotomy that the expected component size is going to be equal to 1 plus t squared and so on. So it's going to be 1 over 1 minus t if t is less than 1. So this is, of course, a summable geometric sequence. But if t is greater than equal to 1, then this expectation is going to be very big. So in that case, the connected components become bigger. And as a matter of fact, if t is strictly bigger than 1, then you can see that, that this sequence grows exponentially. So something very wild happens. And well, if t is equal to 1, then still this expectation is big, but it at least the number of neighbors of neighbors of neighbors and so on, this thing does not grow exponentially. And here's a thing that I want to mention. So of course, this talk is about a certain natural catastrophe, namely forest fires, but of course now everyone is concerned about a different type of catastrophe, namely epidemics. And there is an analogy here with this thing that they call the reproduction rate of an epidemic. If you remember, the reproduction rate is the following number. How many new people do you contaminate while you're contaminated? And if the expected number of people that you contaminate is bigger than 1, then there's a danger of epidemic, because, well, if on average I contaminate 2 people, then those 2 people are going to contaminate 2 more people on average, and so on. So in the second generation, there are going to be 4 people on average, and in the next generation, there's going to be 8, and so on. There is some sort of exponential growth of the epidemic outbreak, while, on the other hand, if the reproduction rate of your epidemic is smaller than 1, then you contaminate on average less than 1 person, and even if you do, then still somehow the same calculation shows that that there is not going to be a big epidemic outbreak. So that's this dichotomy is present in random graphs, and of course in the science of epidemics. And of course, if you've learned about branching processes, then this is a very familiar phenomenon. But I don't want to talk too much about branching processes here. So this was a little crash course on the Erdős-Rényi graph and its phase transition. And the message is that all you need to know is the expected number of neighbors, the expected number of occupied neighbors, and if that number is bigger than 1, then there is a giant component, but if that number is smaller than 1, then there is no giant component in the Erdős-Rényi graph, and components are small. So now I can finally return to the forest fire model. So if you remember, there was this parameter lambda n, which the lightning rate per vertex was lambda n. And now I want to talk about an assumption that we make, namely so imagine that there is this n and it's very big. So actually I want to think about a sequence of forest fire models that are getting bigger and bigger. So imagine a forest fire model on 1,000,000 vertices, but then throw that away and imagine a forest fire model on 10 billion vertices and so on. So n is going to get bigger and bigger in our head. And I want to talk about in some sort of limit when n goes to infinity, when the lightning rate is the lightning rate per vertex is much bigger than 1 over n, but it's much smaller than 1. So what does this mean? We assume that n is very big, n goes to infinity, but we assume that lambda n is much smaller than 1, so we assume that lambda n goes to 0. This means that the lightning rate per vertex is so small that small connected components do not really get hit by lightning. So in a reasonable time frame, you will never see, so if you choose a particular connected component of size 5, let's say, then it's not going to get hit by lightning because the lightning rate per vertex is small. Therefore, as long as your connected component is bounded, it's not going to get hit by lightning. On the other hand, we assume that lambda n is much bigger than 1 over n, and that means that n times lambda n is big, n times lambda n is infinity. That means that a giant cluster is going to be destroyed immediately, or it would be destroyed. Because if there is a connected component whose size is comparable to n, then each of those vertices receives a lightning with rate lambda n. So the total rate of lightning that this connected component receives is already n times lambda n, so that's very big. So that means that component is going to be destroyed immediately. So that means that our fire somehow does not even allow giant components to be born. Therefore, this is the message here, that the model exhibits self-organized criticality. These fires, if the lightning rate is in this range, then somehow the fires will never allow a giant component to be born. Or more specifically, so if t is less than or equal than 1, then the fires do very little harm. So if t is less than or equal than 1, then this graph with the forest fires is just going to look like an Erdős-Rényi graph at time t. Why? Because the fires do very little harm to this graph, since it is subcritical anyway. So if it's subcritical and there are very few lightnings, then maybe you will see a couple of fires here and there, but not so much that it changes the big picture. So as long as your graph is in the subcritical state anyway, then the fires do not do too much harm. On the other hand, something completely different happens when t is greater than or equal than 1. Then lightnings do not allow giant components to be born. As a matter of fact, what happens is that giants constantly try to born, these giants constantly try to form, and they are constantly destroyed by the fire. And as a matter of fact, what happens is that if t is greater than or equal to 1, then these dynamics keep this graph critical in some sense. It's going to be critical in a similar fashion, that it has no giant component, but still it has some properties that are shared, that are very similar to the critical Erdős-Rényi random graph. However, these graphs that you see at a time which is bigger than 1, in the Erdős-Rényi graph, these are going to be critical in some sense, but the picture is going to be a bit more complicated than the critical Erdős-Rényi graph. So it's not that you see a critical Erdős-Rényi graph for t equals 2. You're going to see a graph which is a bit more complicated, but still it's going to be critical. And the rest of this talk is about this. So I will try to explain this complicated stuff. So I will try to explain what it means for a graph to be critical, if it's not the Erdős-Rényi graph. And again, this is going to have also some analogies with epidemic models. So if you're interested in epidemics, then stay tuned for the rest of the talk. So I want to talk about the structure of this graph in the forest fire model. And a very important quantity that's going to play a role is the age of a vertex at time t in this graph, that I'm going to denote by A, where A stands for age. The superscript n is a reminder that we are in a graph with n vertices. The subscript t is a reminder that we are talking about what we see at time t, and the v is my vertex. So the age of a vertex is the time that has elapsed since the last time that my vertex burned. Or if it has not burned at all, then then the age is equal to t. So either the time that has elapsed since the last burning time, or the time that has elapsed since time 0. And then the philosophy is that the older the vertex you have, the bigger chance it has to be connected to other vertices. So the older the tree, the more inflammable edges build up around it. So here's a lemma that is kind of the basis of the rest of this talk. So this is like the central observation, and it's a bit technical. So if you condition on all of the ages that you see up to time t for all of the vertices, so if I allow you to look at the ages of the vertices, of all of the vertices up to time t, so you have all of this information, but if I do not tell you anything about the location of the edges, I only tell you about when the fire happened. So imagine that you're the fire brigade, you're the fireman. You do not see the inflammable edges. All you see is the last time for each vertex when it was burned. And what I see is that based on this information, still you can make a very nice educated guess about the graph that you see at time t. So if you're only given this information, then the probability that a particular pair of vertices, v and w, are joined by an edge in the graph that you see at time t, conditional on this information, it's going to be 1 minus exponential minus 1 over n times the minimum of the ages of the endpoints. Or again, if I use a very similar approximation as before, since n is very big, I can just say that the probability that two vertices are joined by an edge at time t is just the minimum of their ages divided by n. And what is even better is that given this information, these edges are present independently with these probabilities. So this is believable. The more time, so if both, so if you look at the time, where both of those edges so this is okay, it's hard to explain. So this is the length of the time interval that happens since the last burning time of either end vertices and now, and since the edges appear with rate 1 over n, it makes sense that this is the probability that an edge is present between two vertices with this age. Okay, so I'm not going to tell you more about this. What I will tell you about is that now you have a graph, and this is no longer an Erdős-Rényi graph because different vertices have different ages, and based on the age, there are different probabilities at which they can be connected. So, so the question is, if you're given such a graph, how do you determine if such a graph is subcritical or supercritical or critical? So let's try to figure this out. And as a matter of fact, we are going to go a bit more abstract. So what's going to happen is we define a more general model, which is called inhomogeneous random graph, and it goes like this. So there is, in order to define an inhomogeneous random graph on n vertices, you are given a kernel that's going to somehow describe the probability of edges based on the types of vertices. So kernel is just a function which takes two numbers and gives a positive number, and it's a symmetric function, so kxy is going to be equal to kyx. And so how to generate an inhomogeneous random graph. You generate it in two stages. In the first stage, you assign a type to each vertex. And in our case, in our special case, the type is going to be the age of the vertex. And as soon as you're given the types of the vertices, you can generate the graph. Conditional on the types of the vertices, the probability that vertices v and w are joined by an edge in this graph Gn is going to be 1 minus exponential 1 over n minus 1 over n times the kernel value of the type of one of the n vertices and the type of the other n vertex. And again, I use this usual approximation. So again, the probability that an edge is present is, it depends on the type of the n vertices in the way that you take the kappa function of the type of v and the type of w, and you have to divide by n. And of course, the edges are present independently given in the second stage. So given the ages, you just draw the edges independently with these probabilities. So what I defined is called an inhomogeneous random graph, and it was introduced by Bollabás, Jansson, and Riordan in 2007. So roughly 50 years later than the plain Erdős-Rényi random graph. And of course, the Erdős-Rényi random graph is a special case where every vertex has the same type. So if every vertex has the same type, then the graph is homogeneous, and we call it Erdős-Rényi graph. But if different vertices have different types, then this random graph becomes inhomogeneous. And of course, the special case of the forest fire model that I explained on the previous slide is when this kappa kernel is just the minimum. So in that case, you just take the minimum of the two ages, and that's going to determine the kappa value that appears in the numerator here. And of course, the same question stands. If you're given an inhomogeneous random graph, how do you decide if it is subcritical or supercritical or critical? So does it contain a giant component, or are the components very small? And here's a little calculation. So this is, so strap in your seat belts. This slide is going to be the mathematical part of this talk. So this is going to be the calculation, the hardest calculation of this talk. So I hope you're ready. So, but actually it's going to be a bit simplified. So let me assume that there are only 5 types. So I don't want many types. Let's assume that there are only L types, and let's denote them by A1, A2, and AL. Each of the vertices in my graph has a type which belongs to this set. And let me further assume that the number of vertices with type AI is equal to pi times n, where of course this pi is the fraction of vertices with type AI. And of course, if you sum up these fractions, then you get 1 because each of the vertices have a type and only one type. So if you so this is what we call the type distribution. So this pi distribution is just the distribution of types. And once again, pi I is the fraction of vertices with type AI. Now, I want to repeat my previous calculation that I did with the Erdős-Rényi graph, but now I need a bit more complicated notation. So if I have a vertex V which has type AI, let me denote by zkij the number of vertices with type AJ which are at graph distance k from my vertex V in the graph. Okay, so I'll let that definition sink in. So in particular, if k is equal to 1, and if I have a vertex V with type I, then z1ij is just the number of neighbors of my vertex V which have type AJ. So let's begin with this. Let's try to calculate the oops, oh no. Oh, I accidentally pushed the end button. Okay, so once again, z Z1ij is the number of neighbors of a vertex with type I which have type j. And I want to calculate again the expected value of this random variable. So let me denote by aij the expected value of this random variable. And how do I calculate that? So this pi j times n, this is the number of possible neighbors. So this is the number of vertices with type j. And if I have a vertex with type I, then the probability that I'm connected to that particular vertex with type j is, of course, the kappa aij divided by n. And of course, these two terms cancel out, the two n's cancel each other out. So what I obtain is that the expected number of neighbors with type aj is equal to this formula, kappa aij times pi j. And I want to define a matrix. I want to define the matrix which has size L by L. Remember, L is the number of times. So I want to define a matrix, it's a square matrix, where the entry in the ith row and jth column is this number aij. Again, I have a question to the audience. Now that I define this matrix, what do you think? If I want to calculate the expected value of Z2ij, so again, if I look at the cousins, so Z2ij is the number of neighbors of V which have type aj. What do you think? How am I going to express the expected value of Z2ij using this matrix? So this is kind of a little rhetorical question. What am I going to do with this matrix? What do you think? Again, the fastest answer was Eper Miklós. So indeed, if you take the expected value of Z2ij, that's going to be, you take the square of the matrix A and look at the entry indexed by ij. This is quite easy because you have to sum over all possible intermediate vertices. I don't really care about the type of the intermediate vertex, so I have to sum over that, and that's exactly how matrix multiplication works. And quite similarly, if you look at the expected value of the number of vertices which have type aj and they are at graph distance k from my favorite vertex with type I, that's going to be entry indexed by ij of the kth power of my matrix A. So it was very handy to define this notation, but now given this little calculation, now I want to decide about whether this graph is subcritical or supercritical. So here's my next rhetorical question of this audience. Remember, in the case of Erdős-Rényi graph, if the expected number of neighbors was less than 1, then my graph was subcritical. If the expected number of neighbors was bigger than 1, then my graph was supercritical. How about the case of inhomogeneous random graph? What do you have to look at to determine whether your graph is subcritical or supercritical? Here's a hint. You have to look at this matrix, and you have to look at a quantity associated to this matrix, and that quantity is going to determine whether the graph is subcritical or supercritical. So what is your guess? What do I have to look at? Oh shit. I hope. Ezt még csak pillanat.
Az semmi.
Az semmi. Ah. Oops. Well, I hope you can still hear me. I hope that my internet did not get disconnected. So did you hear my little question?
Megy.
Okay. Okay, good. So the answer to my rhetorical question is that you have to, in order to see the phase transition of the inhomogeneous random graph, you have to look at eigenvalues. So and here is where you need the Perron-Frobenius theorem. It says, the Perron-Frobenius theorem says that if you have such a matrix, if you remember, A is a matrix with non-negative entries, and if you have a matrix with non-negative entries, then it's going to have an eigenvector, and the eigenvector corresponding to the principal eigenvalue, the largest eigenvalue, is going to have non-negative entries. So once again, Perron-Frobenius theorem states that if you have a matrix with non-negative entries, then the largest eigenvalue is going to be non-negative. It's going to be a positive real number, and actually the eigenvector corresponding, the right eigenvector corresponding to this eigenvalue, is going to have non-negative entries. And in my case, let me denote this by theta. So let me denote by theta the right eigenvector. So in matrix notation, A times theta is equal to lambda times theta. So that's the definition of an eigenvector. And to write it out in detail, this is just matrix multiplied with the eigenvector. It's going to be so this is just the equation that needs to hold for entry j for this eigenvector. Of course, remember the matrix was kappa ai aj times pi j. And what I claim is that if the principal eigenvalue of this matrix is smaller than 1, then you're in the subcritical phase, and therefore the expected component size of your favorite vertex is going to be of order 1, so it's not very big, and as a matter of fact, the largest connected component is going to be of size log n, so the components are small. The lightning doesn't do too much harm in this case, but if lambda is strictly greater than 1, then your inhomogeneous random graph is in the supercritical phase. In this case, there is a giant cluster whose size is comparable to n, so a positive fraction of the vertices is in this giant cluster. And here's a little remark that I should have made earlier. So even in the supercritical phase, if you remove the giant cluster, the rest of the graph looks like a subcritical graph. So if there is one unique cluster which is huge and the rest of the clusters are small, just like in the subcritical graph. And so this is the dichotomy. The whole graph, the behavior of the graph is nicely encapsulated by the behavior of the principal eigenvalue. And of course, if lambda is equal to 1, then weird shit happens. So that's the critical point. Then the size of the maximal connected component is much bigger than log n, but much smaller than n. And the expected size of the cluster is big, but much bigger than the size of the biggest cluster. So that is somehow the threshold point between safe and dangerous zone, or otherwise put the subcritical and supercritical phase. So now, given this knowledge, I can finally talk about the self-organized criticality of the forest fire model. But before that, I have to do one more thing. So this is just a reminder. So theta is the right eigenfunction of this matrix, or eigenvector of this matrix A. And if you write it out in detail, this is the equation that the ith coordinate of the right eigenvector has to satisfy. Oh no. Maybe I mixed, okay, so probably this equation is okay, but the previous had a typo in it. Oh, well, whatever. So I think this is the good equation, and the previous one had a typo. And of course, you know very well that if you take a constant multiple of an eigenvector, then you get an eigenvector. So I want to normalize my eigenvector in a certain way, so I can assume that my eigenvector satisfies this equation. And then actually it's going to be uniquely defined. So that's part of the Perron-Frobenius theorem. It's that if this matrix is irreducible, whatever that means, then actually there is a unique eigenvector satisfying these properties that I listed here. And then I want to say one thing. I want to say one more thing. I want to talk about the distribution of the ages in this inhomogeneous random graph, or the distribution of types. So if I define mu I to be theta I times pi I, and I make a vector out of these quantities, then actually this vector mu is going to be the left eigenvector of my matrix. So the left eigenvector and the right eigenvector look very similar, and that's because the kernel is symmetric. So it's, if this was a symmetric matrix, then the left eigenvector and the right eigenvector would be the same. But since it's a little bit different, then you have to adjust the right eigenvector to obtain the left eigenvector. So this mu is a left eigenvector, and therefore mu A is equal to lambda times mu. And of course, the normalization that I obtained here translates to this. So this mu is, of course, a vector with non-negative entries, and those entries sum up to 1. And what I want to say is that if my matrix is critical, so if the principal eigenvalue is equal to 1, then quite similarly to what you've learned when you've learned about Markov chains, then this sequence of matrices, so if you look at the kth power of this matrix and you let k go to infinity, then this matrix converges, and it converges to a matrix where all of the rows are equal to this left eigenvector mu. And this is, of course, okay, now just a quick reminder. So if lambda is less than 1, then of course this limit is equal to the 0 matrix, and if lambda is greater than 1, then somehow this limit blows up. But if lambda is exactly equal to 1, then this sequence of matrices converges, and it converges to a matrix where all of the rows are equal to mu. And, well, heuristically, this describes, or this is an explanation of a fact that I want to use later, namely this mu. This is a probability distribution, and I claim that this distribution mu is the type distribution of, or the distribution of types in large clusters of the graph. So if you look at a very large cluster of this graph, then the distribution of types is going to be described by this vector. So the fraction of vertices inside that large cluster which have type A1 is going to be mu1, and so on. The fraction of vertices with type AL is going to be mu-L. And as a comparison, the pi, remember, so this pi, if you put the fraction of vertices into one vector, then pi is the type distribution of vertices in the whole graph, but pi is different than mu. So pi is our type distribution, but this mu, this is the left eigenvector, and the pi describes the type distribution in the whole graph, where mu is the type distribution in large clusters. And the reason why we are interested in large clusters is that those are the ones that get destroyed by the fire. So in the forest fire model, recall that it's an inhomogeneous random graph where the kernel is the minimum of the two edges at the two endpoints. So just rewriting the previous equation. So if you look at the eigenvector theta, then it has to satisfy this equation, but we still use this normalization. So there is a unique eigenvector satisfying this equation due to Perron-Frobenius. And now, if you remember, we had this lemma that the graph that you see in the forest fire model at time t, that graph is going to be an inhomogeneous random graph. So in order to describe this graph or to understand this graph, all you need to understand is the distribution of the edges inside the graph. So that's why I want to introduce the empirical age distribution in the graph that you see at time t. So this is a little notation. So this is going to be a probability distribution where I put mass 1 over n at every age that appears in the graph. So I sum over all vertices in the graph, and I put a Dirac mass at the age of that vertex, but I multiplied the whole thing by 1 over n. So this is just what we call the empirical age distribution of the graph. So this is a probability measure. It's a random probability measure because you look at a random graph, you look at your random graph has a random age distribution, and therefore this is a random probability distribution which has n atoms, and each of the atoms has weight 1 over n. So this is the empirical age distribution, but somehow the behavior of my inhomogeneous random graph that I see at time t in the forest fire model, that the behavior of that graph is encapsulated in this age distribution. So I want to understand this if I want to understand the self-organized criticality of my model. So here's the theorem. Here is the main result of this talk, and here is the main result of the paper on which this talk is based on. This empirical age distribution converges to some age distribution if you let n go to infinity. So if you look at a sequence of forest fire models that get bigger and bigger, but still you look at them at the same time t, then for each fixed time t, this distribution converges weakly. And this limiting age distribution that describes the age distribution that you see in very large graphs, the question is, how do you decide if this age distribution or the graph corresponding to such an age distribution, how do you decide if it's subcritical, how do you decide if it's supercritical, or how do you decide if it's critical? Well, it's intuitively, it should be obvious that you have to look at the equation that we have at the top of the page, and we have to replace the sums with integrals. So in this case, you no longer have an eigenvector, but you have an eigenfunction that we denote by theta, and it's going to be a positive continuous function. And the defining equation of the eigenfunction, instead of a sum, you have an integral, and you integrate the minimum of these ages, and then the eigenfunction appears, and of course, you integrate this whole thing against this age distribution that you have at time t, and then has to be equal to lambda t times the value of the eigenfunction evaluated here. And this lambda t is going to be the principal eigenvalue at time t. And of course, the normalization also changes to a formula with integrals. So there is this integral, the integral of the eigenfunction with respect to the age distribution should be equal to 1. So it's just the continuous analog of the equation that we had previously, and this lambda t is going to be the principal eigenvalue corresponding to this linear operator that I did not even describe here. So the important thing is that analogously, if there is a theta satisfying these equations, there is a unique one that's again guaranteed by the continuous version of Perron-Frobenius. If that eigenvalue is less than 1, then your inhomogeneous random graph is going to be subcritical. If the eigenvalue is bigger than 1, then your inhomogeneous random graph is going to be supercritical. And if the value is 1, then it's going to be critical. So here's the main result, which is self-organized criticality, as I advertised before. If time is less than 1, then this age distribution is very simple. It's just going to be Dirac mass concentrated at t. So if n is very big, then, and if t is less than 1, all of the vertices are going to have age t at time t, or almost all of them, meaning very few of them have been affected by lightning, meaning that the age of almost all vertices at time t is going to be t. And in this case, if all of these vertices have roughly the same type, then actually we are talking about an Erdős-Rényi model. So remember, an inhomogeneous random graph where all the vertices have the same type, that's a homogeneous random graph, and that's called an Erdős-Rényi graph. And in this case, the principal eigenvalue is just equal to this value t, on which your probability measure is concentrated on. And if t is less than 1, then this is less than 1. And as we have discussed before, this is the subcritical case. So in this case, there are you are safe from fires. But here is the interesting thing. As I said before, these fires do not allow your giant component to be born. So when t is greater than equal to 1, then for all values greater than t, this eigenvalue is going to be constant 1. Remember, in the Erdős-Rényi graph, the lambda t is equal to t, so that's bigger than 1, that's the supercritical, but not in the forest fire model. For all values t greater than equal to 1, the principal eigenvalue is equal to 1, so the graph remains critical. So this is self-organized criticality, and this was a long story, but the end of the long story is that now I could give a roughly precise definition of this model and how it exhibits self-organized criticality. And there is more. This is the last slide, by the way. So thank you for sticking with me for such a long talk. Now the rest of the talk is going to be a bit technical, but I just want to tell you what we know about the age distribution. So as I said, if you want to understand the graph at time t, all you need to understand is the age distribution at time t, and that's what I call t. So when n goes to infinity, this is the limiting age distribution. And of course you want to understand how it evolves in time, and what I can say is that we can prove that this age distribution satisfies a funny differential equation. It's a strange thing, because this is a differential equation for probability measures, but somehow it's a differential equation, so in theory you could solve it, but of course we do not have an explicit solution for it. But at least let me try to explain the terms of this differential equation which describes the time evolution of the age distribution. So first of all, there is this first term, which is just a fancy way of writing a transport term. So this just says that if nothing else happens, then the ages in the graph increase at speed 1. As time elapses, the trees grow, so the age of each tree gets bigger, so this probability distribution gets shifted to the right. And this is the PDE way of writing this. So this, I don't want to get into these details. It was a co-author who came up with this, but this is just me. So if your partial differential equation would be only this, that would just mean that this probability distribution gets shifted to the right, namely every age increases at speed 1. There is this other term, mu t, that appears, and this is going to be the left eigenfunction, or more like eigenmeasure. So this mu t is going to be the age distribution in the large connected components, and the way to describe it is that the Radon-Nikodym derivative of the age distribution in large components with respect to the age distribution in the whole graph, that's described by the right eigenfunction. This is the analog of this equation that we had here on the previous slide. So there's a very simple equation connecting mu and theta and pi, and the continuous analog of that equation is the one that's written here. The moral of the story is that mu t is the age distribution that you see in large connected components at time t. And then there is this one more term that I denote by phi of t. This is just the instantaneous burning rate. So this is the rate at which things burn. So, you know, lightnings. So we are in the forest fire model. So there are fires happening, and phi t and this phi of t describes the rate at which things burn. And the good news is that we even have a formula expressing this phi of t in terms of the age distribution and this eigenfunction. And then this term is with the minus. This is, so in order to describe the evolution of the age distribution, you have to take into account that vertices burn, and if a vertex burns, then its age no longer contributes to the age distribution. So this term with the minus sign corresponds to the burning of types. So since there is burning, this burning makes the types disappear. And of course, it's going to be a constant multiple of the age distribution that you see in large connected components. And of course, this last term, this is as soon as a vertex burns, then of course its age becomes 0. As soon as you burn, you're reborn, and now you have age 0. So this is the whole mass. So this is just the Dirac delta. So all of the mass that's burnt at time t reappears at time with age 0. So of course this was very complicated, but the message here is that, at least in theory, we can describe the evolution of the ages using a differential equation. And this is the end of this talk. So this talk was based on this paper, and you can, if you're interested, you can find it linked on my webpage. So I think this is the end. And now, if you have any, if you're still there, then you can ask questions in the chat box. Ennyi oké? Okay, so maybe I should keep talking, because I can see that that there is a delay, so I'm still giving my talk. So you could not even hear my question. But I'm eagerly waiting. So as soon as you pose your question, maybe I can immediately answer it in the chat box. Or I can answer it verbally. Ah, the function k was a little bit mysterious to me. The function k was function k was a little bit mysterious to me. Isn't there any convention for it? What kind of function can it be? Function k? You mean kappa? The kernel. Okay, so Miklós Eper has a question about the kernel. That was so we are talking about inhomogeneous random graphs as they were defined by Bollabás, Jansson, and Riordan. Well, the kernel can be any continuous function. This is my favorite kernel here, the one where it's the minimum of 2 values. Well, okay, maybe it should be continuous and it should be bounded. Yeah, that's it. But what are other famous inhomogeneous random graphs? Well, if the kernel evaluated at xy is a product of a function of x and the product of a function of y, that's kind of a famous special case. Those are called rank 1 models. So if your kernel is the product of a function of x and the product of a function of y, then of course this matrix A is going to be a rank 1 matrix. So it's a matrix which has rank 1, and of course in that case it's very easy to calculate the kth power. In that case it's very easy to determine the eigenvalues. So that's a kind of a very simple special case. Otherwise, maybe if you can elaborate on your question, then maybe I can answer it more specifically. A gépen. So if you have further questions, please ask them now. Or say goodbye on the chat wall and log out. Most már nem lesz több kérdés, jó? Jó. Okay, so thank you for your attention, and it's time for me to say goodbye. So thanks for attending this talk. Don't forget to fill in the attendance form. Bye bye.